Hi, everyone. I'm Ellie Feit. I'm a senior fellow of Wharton Customer Analytics. I've been involved in Wharton Customer Analytics for 10 or 11 years now, something like that. And I'll be introducing your next two lightning talks. So first up, we have Adi Weiner and Jack Sawslaw. There's a misspelling in the program that is tripping me up. Sorry about that. So Adi is a professor here at the Wharton School, and he's the chair of the undergrad stats program. He's had a long-time interest in sports analytics, and some of you may know him as the host of Wharton Moneyball on Sirius XM Radio. Jack, I'm more excited to introduce Jack. Jack, I've known Adi a long time, but Jack is graduating this weekend from the Wharton School in stats and entrepreneurship. Can we all give him a round of applause for that? He'll be joining Facebook as a data scientist, which is equally impressive. And last but not least, he was the kicker for Penn football. Go Quakers! And they are going to tell you a little bit about their participation in the NFL Big Data Bowl.
Thank you. So it's going to be my pleasure to introduce Jack, who's going to do the main body of the actual analytic portion of our talk, and I'll just interject. But before we do that, I want to tell you a little bit about statistics at the University of Pennsylvania, particularly at the Wharton School. As Eric told you earlier, the Wharton School has had the statistics department for the entire university housed in its buildings since it's the very beginning, which does put us in a unique and position in the fact because we are there. The stat department is concentrated in Wharton. But it was always kind of a funny business for me as a statistician, and I've been at Wharton now 20 years, because we always asked ourselves, what are we doing here? Why did we ask ourselves that 20 years ago? Because frankly, the role of analytics in business was nothing like then what it is today. And while we were methodologists, that is the people who invent the techniques that you now are using, many of us were analysts. And I'm going to rebut Charles, who told you earlier that the word data analyst is redundant. You could throw out the word data, because when you're talking about analysts, you're of course talking about data. But that would have been news to me 20 years ago, because I was an analyst in communication systems, and I did it entirely through mathematics without a drop of data. And that's where we did analytics back then, but things have accelerated enormously from the time where there was essentially no majors or concentrators, as we call it in the statistics universe at Wharton, majors in the MBA program, at the university at all. And in fact, when Eric he just told me earlier, when he was a student here at Penn, he was the sole concentrator in Wharton in statistics, and he was able to pull that off because he took PhD courses, because we didn't have any other courses for anyone to take. That is amazingly different today. There's now the subject studied by hundreds of people across Wharton, the college, and engineering. There are hundreds of Wharton statistics concentrators, not to mention the several hundreds of what we call business analytics, which is a new analytics, a new concentration that we created, which is really an amalgam of statistics and kind of data engineering through the OID department. And there are also a data science minor in the School of Engineering. So there's a huge number of students who are interested in learning about analytics. Because you have a giant base of students at the bottom, now you have to find something for them to do at the mid and the upper levels. So what I did was I took about 20 students who are particularly interested in what we call sports analytics. Now, what is sports analytics? Most of you understand. This is the success. This is how the Red Sox managed to toss the curse, by investing in statistics. Maybe the Eagles managed to win the Super Bowl also by investing in analytical systems and decision making. But one of the things that's great about sports, and particularly to teach statistics in the context of sports, as we heard from many of the speakers, there's nothing more important to applying analytics to understanding context. And when you deal with high school and college students, and I teach high school as well as college students, they don't really have context. But they do, many of them, understand and love sports. So it's a great way to introduce mathematical ideas, statistical ideas, and programming ideas in an area that's just a lot of fun. And so 20 of us, including Jack, and including several people who are here, Jennifer and Jake, meet with me most afternoons on either Monday or Tuesday, and we talk about applications of statistics into in sports arenas. So The Big Data Bowl. This was something that the NFL was producing and pushing in the middle of December. And if you know the calendar, that means the school students aren't even around, in an effort to try to get people to invest in the new massive amounts of data, which you'll hear about in a minute, and apply it to NFL or football-oriented problems. And in fact, I was talking with Eric and Mary, and we said, wouldn't it be great to have a student team enter this competition? And my response was, how can that possibly be? They're not going to be back until January. They'll have 3 days to produce a project. The data is immense, and they couldn't possibly do it. Well, couldn't have been more wrong. So there was a group of students. Let me see if I can find their pictures. There they are. Andrew? Did you?
I did not cut them out. I have no idea.
All right. So there were a group of students. There was Jake, who's over there. Eric Dong, who's actually from the School of Engineering. Andrew Castle, who's missing. And Jack, and then through my advising through our program, entered this competition. I'll just tell you a little bit about it. The time frame wasn't ideal. They had basically 4 days to put it together. Data was immensely complicated, and you're going to hear about the data in a minute. It was what we call a classic big data problem. What does that mean? We have hugely complicated high-resolution video data, which is then, of course, merged with all the play-by-play data and the player and team and outcome data that's all has to be processed and engineered into solving a problem. So what was the problem? They were asked by the NFL to pick one of 3 possible really mathematical or statistical tasks. One would be to evaluate player speed. Now, there's a lot to running with a football or without a football other than acceleration and just top speed. And the charge was figure out something other than those 2 kind of characteristics to help describe the importance and use of speed on the football field. The second was optimizing receiver routes. So a running back sometimes catches a tight end or a wide receiver, has to run somewhere to get the ball, and they run a pre-described or sometimes ad-libbed route, and some routes are more effective than others, and that was one of the asks, to figure out what's the best route to run in a given play. The third possible ask was suggest a rule change that might be beneficial for some purpose, maybe to make the game safer. So these were the 3 asks, and our students chose the middle one, optimizing receiver routes. So I'll take you over. I'll let you go, and I'll kibitz.
Awesome. All right, thank you, Professor. So, as Professor noted, the data was immensely complicated, but we were only given a certain set amount of it. We were just given the first 6 weeks of 2017. We were given game level data, like how teams did in that game, who won, player level data, who the players are on the field, play level data, how each individual play in that game went, how many yards they got, was it a pass, was it a run, and then finally the gold mine. This was where all the complication and pretty much part of the reason why we wanted to do this project was just to get access to this player tracking data, which is video data that is turned into a spreadsheet. So what we have here are essentially X and Y coordinates, the distance that you've run, and then S which is like your angle. So they track this data by a chip on the front of your shoulder pads, and every single moment you walk or run, every 1/10 of a second, they track your location, your angle, how far you've gone, and so on. It's a lot of information. We get hundreds of thousands of these data points per game, and we had 16 games per week, and we had 6 weeks. It ended up being lots and lots of data for us to get into in 3 days. Yeah. So the first thing in any problem is data exploration. As Professor Weiner said, the problem that we wanted to solve was optimizing receiver routes. So what we first wanted to do was figure out where receivers on the field before they start. So at the top here, you see this big line of dark blue. That represents the line of scrimmage. Everything beyond that is where players line up. So players line up behind the line of scrimmage. What we're tracking here is the density of players and receivers behind the line of scrimmage. So receivers are wide receivers, tight ends, running backs. As you can see, those 2 high-density nodes in the middle, that's usually where tight ends line up. On the outside is where wide receivers usually line up. And then in that middle part, in the back, is where running backs line up. So next step is data exploration and data cleaning. So we're looking at receiver routes. Let's look at all of the routes run by Alshon Jeffrey against the Kansas City Chiefs. So what this graph represents is we have this line of scrimmage in the backfield here, but imagine Alshon Jeffrey is in the backfield at one single spot, so we made him start at the same spot on every play, And these tracks all of his routes in that game. So he runs up, he cuts to the right, he runs up, he cuts to the left, he runs up, and still keeps on running. What these dark blue, they represent receptions. The slightly less dark blue are targeted, and then these light blue are empty routes where he runs a route and he isn't targeted on the play, someone else is. So the problem we were trying to solve is essentially, what are the best routes to run on any given play? Essentially, if we had a play in a game, I want to tell the offensive coordinator, hey, run this route, this route, this route, and this route in order to optimize how many yards you get. This is a very hard problem to solve, and offensive coordinators know this a lot better than me. But we're trying to figure out how we can apply this data to make better decisions on the offensive end. So the first thing we did was shape-based clustering. What this resulted in is essentially trying to figure out what routes are on the play. We have a route and its shape, and we're trying to figure out how we can group similar shapes together to represent similar routes. And then the second part is once we know what route to run, using machine learning to figure out what are the best routes to run in any situation.
So this shape-based clustering, just to interject, is very important because the data is absolutely massive, and you just can't run a statistical algorithm on a massively giant data set and expect good results. So the idea was to reduce it down, the dimensionality of the data set, and the shape-based clustering, which you're going to hear about, was just the final effort that they made. They went through several other approaches before they converged on this particular solution. And by the way, this happened about a day before submission, so it's pretty accelerated time frame.
Yeah, exactly. So this is a route. We have a route. Some guy runs from the start of the left of the quarterback and then cuts off to the right and maybe curls back a little bit. It's this weird shape. What we're doing is we're describing the shape by a bunch of features. For example, where you start, where you end, how far you've run, if you curled back, and then also a lot of measures to capture the curviness of the route, such as the residuals between the start and end point and a bunch of other measures like that. And then we group these routes based off of these similar characteristics. So for example, on the left, we have a 10-yard crossing route. What this red represents is the most common of a 10-yard crossing route, where all of these little black feathers, it might be hard to see, represents all of the routes that are in this cluster. As you can see, they're all fairly similar, and we are very excited to say that we think the shape-based clustering worked very well in grouping together similar routes. For example, for a 10-yard crossing route, we see the majority of them being run by wide receivers and tight ends, less often by running backs. Where on the right, we have a running back out route where the running back starts in the backfield and cuts out to the right. And we see pretty much it's almost entirely run by running backs. So this obscure, just throwing all this data at the machine, we can actually get some real representations of routes without characterizing them beforehand.
I will point out that they had a secret weapon here. If I had been analyzing this, I don't think I would have done as good a job. Jack actually plays football. So that gave him some insight into the little curly cues and activities in these routes which were important in making the features.
Yeah. I'm a kicker.
Well.
So going more into what are these clusters of routes? Let's look at some of the routes run by some famous players. So Odell Beckham, when he was on New York, he runs a lot of curls, slants, stuff like that. These are classic routes that you'd expect a wide receiver to run. Where on the other hand, we have Rob Gronkowski, who's blocking often for Tom Brady, but when he's going out, he's running a lot of seam routes, and then these short curls, which go 5 yards up and then cut back. And then also we see Ezekiel Elliott, who's running a lot of running back outs to the right and left, and then also blocking a lot. The goal here is to show that with this obscure method, we can actually characterize the routes run by players pretty well. So now comes machine learning. We know what routes are run. Now it's trying to figure out what are the best routes to run on any play. So the first thing we did was we split machine learning into two parts. First, figuring out how these routes contribute to how likely you are to get a completion. And then two, once we know how likely you are to get a completion, how many yards are you going to get given you get a completion? Short routes generally give you a better likelihood of completing a pass, where long routes give you more yards given the completion. So we're trying to decouple these two factors when it came to modeling. So we looked at a lot of situational variables, things that you find on the play, and then some of the engineered variables, like the routes run and the position of the players. So let's start with some of the conclusions here. So here we're going to look at two plays. These are two of the first plays of the game. One is between the Broncos and the Bills. The Broncos are orange, and the Bills are blue. And then the second play is the Ravens versus the Raiders. The Ravens are purple, and the Raiders are silver. What we're trying to show in this is on the left, we see a play that gets 2 yards. our models predicted it to get 5.8. On the right, we see a play that gets 52 yards, and our models predicted to get 10.5. Because these are both the first plays of the game, sure, there are a lot of other situational factors like the teams and quarterbacks, the majority of the variance in these predictions were based off of the routes run. So just by clustering and figuring out what routes are run on the play, we're able to figure out and get a better idea of how many yards you're actually going to get. So another thing that we could do is that although our models aren't perfect, we can see a future where we could actually optimize offensive play calling. So let's look at this play here. We're looking at the Cowboys versus the Giants. The Cowboys are in blue, and the Giants are in red. On this play, they get a short completion for maybe 0 yards. If you see number 82, he's on the left side of the screen. That's Jason Witten in 2017. If we changed his route from what we clustered as a blocking route to, say, a short curl, the completion percentage would have gone up by 30%, and the predicted yards would have only, predicted yards given completion would have only gone down 0.1 yards. What this ends up is increasing the predicted yards by 1.65, which gives us hope that with further optimizations, we can optimize an offensive playbook. So what are some of the final quick insights is that 5-yard short curls, 5-yard short hitches are generally successful. So these plays with this route generally give 0.15 more yards on average. And then also another interesting thing what we found is that when it comes to predicting how many yards you're going to get, is that good routes explain more of the variability than good quarterbacks. What I mean by this is that, say you have 5 receivers and all of them stand still in the backfield. It doesn't matter if it's Tom Brady or me. We're getting no yards. But if we have routes designed by Bill Belichick, then it really matters who the quarterback is. So quarterbacks are extraordinarily important, but they're not as important when it comes to predictive variability than as routes. So we had a great time. As we said, we talked about how we turned this around in 3 days. We went to the NFL Combine. I actually texted my parents after I got the notification that we were going to Combine, because I'm a football player, and I was like fairly successful. They had NFL hopes for me. I didn't. I said, I'm going to the Combine, and they were freaking out. But it was for analytics, and it wasn't as cool. So this is us presenting. This is us in front of the poster. Unfortunately, Eric couldn't come, and Professor Weiner as well.
There's Andrew, by the way.
Yeah, there's Andrew. But I guess like the moral of this story is that if you have a really all-star team, we had an all-star team of sports analysts and a professor helping guide us, you can get a lot done in a short amount of time. So thank you.
Well, thanks. That was super exciting, and I know absolutely nothing about football.
You know more now.
But I know more now. Yeah, that one gets the yards. Anyway, I actually wanted to start by a question for you, Adi. How, in analytics broadly, like people are working in all different fields, how important is that domain knowledge for the, understanding? Sometimes I tell my students the process that made this data.
Critical. I teach the MBA core statistics class, and it's tempting, obviously for time purposes, to just jump right in, and we do this. We start teaching methods, and we give examples that are stripped of context. So it is incredibly important to tell people that the first thing one does when we're confronted with a data analytics task is to immerse yourself in the context. And it seems like it's somewhat of a waste of time. If I've got what we call a flat file, as Jack showed you, a big set of rows and columns with labels, just get in there, throw your GBM at it. That's what you did, right? Gradient boosting algorithm. Just get in there in logistic regressions. What do you want? Support vector machine, deep learning, and just chug along. And I think that's exactly the wrong thing to do. The first thing to do is really deeply understand your data, what it's for, what insights, what the problems are, and invest in that. And then your data activities will be much more focused, productive, and useful.
Great. My next question is for Jack. Well, this one's from the audience. Who did the data viz, and what tools were you doing? People were impressed with these animations.
A lot of data viz was done by Jake there.
Jake Wave?
Raise your hand.
But we were also provided, because of the video data, really easy opportunities to track plays. So all of that is
But
made easily available.
What libraries were you using?
Oh, we were using GG Animate and then combined with ggplot2.
Oh, the RStudio
These are
people will
RStudio.
be
Yeah.
happy to hear that they're back in the
We love you
lobby.
guys,
They're
yes.
one of the sponsors of the conference. That was not a setup, by the way. Next question is, I guess for both of you, how do you think having a very short time frame affects how you approach the problem?
Jack?
And actually, it's kind of an interesting contrast to the last speaker who's looking at years of setup for this. You had days.
Yeah, I'd say we were trying to tackle a huge problem in a short amount of time. Like optimizing an offensive playbook is not going to happen in 3 days. But what it did, it made us more focused on what actually mattered, which was getting to something that was useful. So clustering these routes and being able to tell you, hey, these are the routes that are being run is useful in and of itself. So it made us more focused on what was actually useful and less about all the fluff and all that.
Yeah, it seems like you could feed those clusters, like you could show them to kids who are learning to play and say, these are the canonical plays you should learn how to run.
Yeah.
So I'll just respond that one of the things that they had because they had a limited time frame is they actually got it done. There was an end date and they began and they spent all their time on it. And there's some utility in that setup. One of the things that when they immediately spoke to me about what they were doing when I first arrived on campus, I said, well, we can actually probably create a route identification program if we could get what we call a labeled set, which we didn't have. And that would take some investment, and there was just no time to do that. We'll point out that although their presentation was terrific, they didn't actually win, but and they competed in the student division, which also included graduate students and PhD students. So it was quite a formidable task, and they were one of the 4 finalists. But the individual in one of the pro divisions who actually won sat there over the 6-week period that they actually had and watched every single football play and labeled them all, doing exactly what I said you needed to do. You didn't need to label them all. You could probably just done a subset and then built an algorithm. But there's a utility in doing it in 3 days, but there's certainly, of course, no replacement to having the time to actually generate the data that you would really get the most advantageous use out of.
So this is from the audience, of course not from me, because I don't think about football, but can your insights be counteracted by analysis of the defensive plays?
It's a great point.
Yeah.
So one of the things that this analysis doesn't do, say like I tell you to run a short 5-yard hitch every play, is defenses are going to adjust.
Right.
You know what it works only for so long, and they start watching film.
I used to watch Pee Wee football a lot because my daughter cheered, and those guys don't learn very fast, but I'm sure the adults do.
Yeah. And I think that provides a big opportunity, which is looking at how defenses can optimize against offenses as well.
I'll throw in that football doesn't optimize or adapt as nearly as fast as they should. Of the 4 major sports, I think that they're way behind in terms of actually using analytics and implementing it on the field. There are a variety of reasons for that. In contrast, baseball has led the way and has been far ahead of anyone else in doing all that, and we've seen huge changes. Basketball has done an enormous amount in doing this as well, and actually adapting on both sides.
Great. All right, so we're running out of time here, but my last question is for Jack. I saw in your bio that you're starting at Facebook in the fall.
That is correct.
So that means you have a summer free. What are you doing for the summer?
I have a lot of side projects that I'm working on.
Okay.
And opportunity to relax and enjoy my time before I go out into the work world.
That sounds like a great plan to me. Let's thank Jack and Adi.
Thank you.